There are some further exceptions. We start talking about this idea of expanded octets. As it turns out, as you move down the periodic table, from period 1 down, we got period 1, period 2, but then we have period 3, we start to get into the d orbital. And this is a little review for you. When we start getting down to that d orbital, sometimes that d orbital is empty and allows for a little bit more bonding. It allows for more bonds to happen. So expanded octets would be atoms that exist in periods 3 or higher, and they can actually accommodate more than 8 valence electrons. We started talking about this almost day 1 of chemistry when we talked about that third energy level allowing for more electrons to be present. Now, it likes to have 8 electrons. That's a stable state, but it can still accommodate more. So if we look at something like phosphorus pentachloride, that would have a Lewis dot structure that would look something like this. We'd have 5 chlorines bound to the outside, and you'd say, wait a second, that means that phosphorus is going to have 10 electrons. That's too much. Well, it's an expanded octet. It's able to accommodate more than you would normally think. This is going to take me some time to draw this. Look at this. All right. And another example would be sulfur. Sulfur, again, it exists farther down the periodic table. It's got some empty d orbitals that allow for more bonding. And so with something like sulfur hexafluoride, we would have sulfur, and around it we would have 6 fluorines bound. I think these are fun because they start getting a little crazy. Things that we wouldn't expect to see, we start to see here. And again, when you're drawing these Lewis dot structures, we try to keep these in pairs. These lone pair electrons. There you go. So there's 2 examples of expanded octets. Now these exceptions, they are going to now introduce us to some new molecular geometries. We can look at some of the ones that we've seen so far. I mean, if we look at a linear arrangement, we've seen this linear arrangement with binary molecules. If we wanted to look at something like HCl, all right, 1 hydrogen bound to 1 chlorine, that gives us a linear arrangement. But now we know that something like beryllium chloride can give us the same sort of arrangement. So you might have beryllium chloride looking like this. And this, again, would be a linear geometry. If you keep going down, we have trigonal planar, and we talked about boron liking to make that trigonal planar molecular geometry. It's got 3 areas of electron geometry, right? 3 areas of electrons able to bond, but it doesn't have enough to create a new or a full octet. And so when we take something like boron trichloride, we get this trigonal planar shape. It's taking forever to draw these. So we have these different shapes, and there are certain situations where you might have one lone pair. All right, one lone pair that comes that is present, followed by two bound atoms, and in that case we don't have two lone pairs. We only have one lone pair, and so that creates this this trigonal planar bent sort of molecular geometry. So it's going to be very important that when you guys practice these, that you have this presentation open and that you're talking about what are some of the different molecular geometries I can get from different electron geometries or different electron areas that can be involved in bonding. We can talk about the tetrahedral electron geometry, and that gives us these sorry here. Boop. All right. That gives us these different molecular geometries. We've got tetrahedral, which again would be something like methane, CH4. We've got trigonal planar, trigonal pyramidal, and that would be something like ammonia. And then water falls into this bent sort of geometry as well. So the electron geometry is tetrahedral, but because of the way those lone pairs orient themselves, we have different molecular geometries. Now as we move on and we start getting into some different types of molecules, we get trigonal bipyramidal and seesaw and T-shaped and linear and those things. What I really want you to do is to concentrate on this trigonal bipyramidal. Notice that we have one central atom and we have 5 surrounding atoms. So this would be something like phosphorus pentachloride. Okay? And if I wanted to draw a three-dimensional representation of phosphorus pentachloride, then I would put that phosphorus here in the center. All right? I would have one of those chlorines, two of those chlorines on plane with the paper, 3 on plane with the paper, and then one of those chlorines would be kind of jumping out at us, and the other one would be going back into the page. And that would give us this three-dimensional shape, this trigonal bipyramidal shape. So when you have a central atom and 5 peripheral atoms bounding to that central atom, you get this trigonal bipyramidal shape. Then we can talk about when we have 6 peripheral atoms bound to a central atom, then we start getting this octahedral shape. So the example that we've shown today so far was sulfur hexachloride. And if we had sulfur, we know that there would be one of those chlorines on plane, 2 of those chlorines on plane with the screen, and then there would be a chlorine going in, 2 chlorines going into the screen, and 2 chlorines coming out of the screen, giving us this three-dimensional octahedral shape. And so you're going to need to identify what molecular geometry we're presenting to you based on the Lewis dot structures that you're going to construct. So let's see if we can practice a little bit. If I have phosphorus pentafluoride, let's do these together. If I have phosphorus pentachloride, I know that I've got phosphorus as my center atom, and because phosphorus is farther down on the periodic table, it's got that empty d orbital and allows for more bonding, then I would have these fluorines bound to the outside. Awesome. But now I might ask you, okay, well, what then is the molecular geometry. And right from this Lewis dot structure, you might be like, oh, that's not a problem. I understand that. But it might help you to draw in a more three-dimensional sort of way. So I know that 1, 2, 3 of those fluorines is going to be on plane with my page. And then one of those fluorines is going to go back into the plane of the screen, and one of those fluorines is going to come out of the screen, and that gives us this special shape. And this is what we call trigonal bipyramidal. So you'll have to identify what kind of molecular geometry these different molecules make. And you know, if I could actually, I'll show you. Let's see if we can draw this out a little bit. You'll actually see the pyramids, the two pyramids, the bipyramids. We have one that's created between these here. And then we've got one pyramid that's created here. So it's like two pyramids that sort of meet together. Trigonal bipyramidal. If we went and looked at xenon hexafluoride. Well, xenon, again, it's farther down the periodic table, allows for some more bonding. All right, and we could go ahead and throw those fluorines all around the outside of this molecule. Now I'm not going to go and draw the lone pairs. The lone pairs would be much similar to the ones that were up here in phosphorus pentafluoride. But if we wanted to draw this shape, in a way that gives us a little bit better indicator of what the molecular geometry was, we would put the xenon in the middle, okay, and we would have 1, 2 of those fluorines on plane with the page, and then 2 of those fluorines would retreat into the page, and 2 of those fluorines would come out of the page. And we call that octahedral. That's an octahedral arrangement. Now for a little bit more practice, I want you guys to go ahead and try sulfur hexachloride. What you're going to find is that it's very similar to xenon hexafluoride in that those chlorines are going to surround that sulfur in such a way that we get an octahedral molecular geometry. Now you've got a number of new geometries to learn. If you need to pause this, if you need to go back in order to complete your worksheet that we're going to give you, I highly recommend it. If you need to come into class and get a little extra help, please come in. Don't hesitate. Here are some exceptions to the octet rule, things that you might not have expected before, but things that you do need to know for the honors exam. I hope this helped. This is Underwood signing off.